We will use this method of integration for rational functions, and this method is called partial fraction integration, and this is using the process called partial fraction decomposition that you probably learned in college algebra. So remember, this is a way of taking two fractions that have been added together, two rational functions have been added together, and breaking them up. So here is, remember when we find to add two functions together, we had to get a common denominator. And then we're able to add them together. So that we would end up with x minus 4 over x squared minus x minus 2. Now what we're going to do is we're going to take that answer, x minus 4 divided by x squared minus x minus 2, and break it up to the original two fractions. That's called partial fraction decomposition. So, for example, if we had this integral problem, we would rewrite this as the integral of 3 divided by x plus 1 plus the integral of 2 divided by x minus 2. And then we evaluate each of those integrals. For the first integral, I'm going to use u sub, let u equal x over 1, so that becomes the natural log of the absolute value of x plus 1 times the 3. Plus 2 times the natural log of x minus 2 plus c. Okay, so let's review how to do the decomposition of a rational function. Okay, there are a few steps that you're going to follow. The first step is you're going to look and see if the function is improper. If the rational function is improper, then you need to divide. Now remember, it's improper if the degree of the top is equal to or less or greater than the degree of the bottom. I'm going to let little n equal the degree of the top function, and I'll let little d equal the degree of the bottom function. So you're going to divide the polynomials if little n is greater than or equal to d. So to divide, remember you're going to do long division or synthetic division. You're going to get a polynomial plus or minus the remainder over the original divisor. Then you're going to apply steps 2, 3, and 4 to that remainder part. Okay, and just keep the polynomial separate. Okay, now first thing you're going to do is you're going to factor your denominator. You need to completely factor the denominator into factors of the form px plus q to the n power, or ax squared plus bx plus c raised to the n power. Okay, where that quadratic will not factor down any farther. It's irreducible. Step 3 is for all linear factors, you're going to, for each factor of the form px plus q to the m power, the partial fraction decomposition must include the following sums of m factors. If it's a quadratic factor, then each quadratic function will be written in the form of ax squared plus bx plus c to the n power. Okay, so let's look at guidelines if we have linear factors, then we'll look at guidelines if we have quadratic factors. So if our denominator factors to linear terms, the process you'll do is you'll substitute the roots of the distinct linear factors into the basic equation. For repeated linear factors, you'll use the coefficient determined in the above method, and then you'll substitute in some other convenient value of x, something that's easy for you to do, and solve the remaining coefficients. Now this kind of seems a little strange abstractly, so let's look at this example. So we're going to start by finding the factorization of our denominator. So x squared plus 4x plus 3 factors to x plus 3 times x plus 1. So these have two linear factors. So I'm going to rewrite my denominator as a over x plus 3 plus b over x plus 1. So a and b are some coefficient. Okay. Now, we want this to be the same. So remember, to get the same value, we're going to multiply each side. To get a common denominator, I'm going to multiply the first fraction by x plus 1 over x plus 1. And then to get the common denominator, I'm going to multiply the second fraction by x plus 3 over x plus 3. Now, the denominators if I solve this equation and multiply each side by the denominators cancel out. So I can just look at the numerators. So x plus 5 is now equal to a times x plus 1 plus b times x plus 3. Now let's solve this by taking the roots. Now remember, the roots are where our function equals 0. So we're going to set x plus 3 equal to 0 to get one root at -3, and x plus 1 equals 0 to get another root at -1. Then I'm going to go to my basic equation, and I'm going to replace every x with -1. And I'm going to rewrite this and get in terms of a and b. Solving this equation, I find that b must be equal to 2. Then I'm going to repeat this process with the other root. So again, going to my basic equation, I'm going to replace every x. There's our basic equation with every x with -3. And we'll solve this equation for a. And so we can figure out that a must be equal to -1. Then I go back to my partial fraction decomposition, and I replace the a with -1, and I replace the b with 2. So this fraction decomposition of x plus 5 divided by x squared plus 4x plus 3 is equal to -1 over x plus 3 plus 2 over x plus 1. And there's your fraction decomposition. That's what you do if you have linear terms. Next, we're going to look at what if it only factors down to quadratic terms. Well, the process is a little bit different. We're going to expand the basic equation so we can get that basic equation again. But this time we're going to collect terms according to the powers of the x. Then we're going to equate the coefficients of like powers to attain a system of equations involving a, b, c, and however many variables we have. And then we're going to solve this system of equations using our calculator or techniques that you learned in college algebra. So for example, x cubed plus 3 in this example is a cubic that factors to x plus 2 times x squared minus 2x plus 4. And that quadratic, x squared minus 2x plus 4, does not factor. So let's find our basic equation by setting a over x plus 2. Now, since this is a quadratic here, we're going to put the top, remember, we're going to decrease our power by 1, so it needs to be a linear function on top. So we're going to write that as bx plus c is going to be the numerator that you do with any quadratic coefficient. Now, multiplying to get our common denominator, I'm going to multiply the first fraction by the quadratic, the second fraction by x plus 2. Next, I'm going to distribute the a to every term in the first parentheses to get ax squared minus 2ax plus 4a. And then next, I'm going to do the full method to get bx squared plus 2bx plus cx plus 2c. Now I'm going to group everything on the right-hand side by the powers of x. So I have a bx squared plus an ax squared. I'm going to group those together, and I'm going to write that as a plus b in parentheses times x squared. So that's going to be the coefficient of the x squared. Now I'm going to group all my x terms, my linear terms, together. So I have a negative 2ax, a positive 2bx, and a positive cx. So that term, I'm going to add a negative 2a plus b plus 2b, sorry, plus c times x. And then I'm going to group all my constant terms together, which will be my 4a plus my 2c. And now I'm going to make my systems of equations. So my first one is going to be my quadratic coefficients, a plus b, and that's going to equal to what my quadratic term on my left-hand side equals to, but since there's no quadratic term, that's going to equal to 0. And then my linear, negative 2a plus 2b plus c is going to be equal to 1, the coefficient of the x. And then my constant is going to be equal to 3, the coefficient of the constant on the left-hand side. And then I'm going to solve this using either your calculator, system elimination method, any of those methods that we learned in class. So I'm going to do, I'm going to set up my coefficient matrix here, which will be 1, 1, 0, negative 2, 2, 1, and 0, 2. And then I'm going to set up that equal to my B is going to be my answer matrix of 0, 1, 3. And then I'm going to punch in my calculator after I put this matrix in my calculator, the inverse of matrix A times matrix B. And when I do this, my calculator gives me 1/12, negative 1/12, and 4/3. And so that conclusion is that A is equal to 1/12, B is equal to negative 1/12, and C is equal to 4/3. So I can rewrite the fraction decomposition of our original rational function as 1/12 divided by x plus 2 plus a negative 1/12 x plus 4/3 over x squared plus minus 2x plus 4. Now don't worry about these compound fractions. This is okay in this form. You can keep it like this because it's easier to find the integral when it's in this form. So don't worry about trying to simplify those down. Just write them like it is. All right, let's do our first integration problem. So first thing we got to do is we need to figure out the factorization of x squared minus x minus 6. And so when I factor that, I get x minus 3 times x plus 2. And so I'm going to rewrite one factor. I'll write x minus 3 as one factor and x plus 2 as the other factor. Those are linear terms, so I have constants on top. So I'm going to just do an a and a b as my numerators. Okay, and then I'm going to multiply to get my common denominator. So the a term needs to be multiplied by x plus 2. The b term needs to be multiplied by the x minus 3. Since these are linear functions, I'm going to let x equal my 1 root, which is negative 2. Plugging in into my basic equation, x is always negative 2. Simplifying that down, I'll end up with 15, or negative 15, sorry, is equal to negative 5b. Dividing each side by negative 5, I get that b is equal to 3. Then I'm going to let x equal my other root, and so my other root would be x is equal to 3. So going to my basic equation, replacing every x with 3. This time I get 5 is equal to 5a, so a must be equal to 1. So rewriting our integral, I would write this as the integral of 4x minus 7 divided by x squared minus x minus 6 dx is equal to the integral of 1 over x minus 3, because that's my a term, dx, plus the integral of 3 over x plus 2 dx. The integral of this first one is then the natural log of the absolute value of x minus 3. The integral of the next one, the 3 comes out, then it's times by the natural log of x plus 2 plus c. And that's how you do integrals of rational functions. Okay, factoring the top quadratic, I get x minus 3 times x minus 2. Setting up my partial fraction decomp, multiplying each side to get my common denominator. And then plugging in 2 into my basic equation and 3 into my basic equation, I get that b is equal to negative 1 and a is equal to 1. Taking the integral of my first fraction minus plus the integral of my second fraction, I get natural log of x plus 3 minus the natural log of x plus 2 plus c. All right, now here is the first time we have an improper fraction, because notice our degree on the top is greater than our degree on the bottom. So we have to do long division. We have to divide these out. And so first thing I notice is I ask myself, what times x squared would give us a 2x cubed, which will be a 2x. So I multiply each term on the outside of that division sign by 2x. Then don't forget to change your sign. And I end up with x plus 1. So that's my remainder. So I would rewrite this integral as the integral of 2x dx plus the integral of x plus 1 over x squared minus 4x plus 4. And so that second term, that second integral, is the term that we need to do the partial fraction decomposition. So we need to factor x squared minus 4x plus 4, and that factors to x minus 2 quantity squared So this is our first example of what we have is called a repeating factor. And let me show you how we deal with repeating factors. So if I'm going to find the partial fraction decomposition of this, I would rewrite this as my first factor, which is x minus 2. As in the denominator, in the numerator, I'll put a, so a over x minus 2. And then my second one is going to be the repeated factor. So it's going to be x minus 2 quantity squared. Okay, but both of these factors are considered linear. And so they're going to have coefficients on top, a and b. Okay, multiplying by a common denominator, I'll get a times x minus 2 plus b is equal to x plus 1. Okay, now we can do our root. We only have one root this time, which is x equals negative 1. So x equals 2. And I replace every x with 2 and solve for b, and I get b equals 3. Now, because we don't have another root to choose to find our a, we're going to just choose an easy root to work with. I'm going to let x equal 1. 1's usually an easy number to work with. So plugging that into my basic equation, I get that 2 minus a plus b, and then use that value that b is 3. So now I'm going to replace the b with 3 and solve for a. So a is equal to 1. All right, so I can rewrite this problem as the integral of 2x dx, don't forget that term. And then we can break up this second one as the integral of 1 over x minus 2 plus the integral of 3 over the quantity x minus 2 squared dx. All right, so first term is pretty easy to integrate. We know the integral of 2x is just x squared. The second term is also easy to integrate. That's the natural log of the absolute value of x minus 2. And then let's do u substitution for this last integral, letting u equal x minus 2, and so the derivative of u would be dx. So I can rewrite this as plus the integral, 3 times the integral of u to the negative 2 du. And then when we evaluate that last integral, that becomes at 3 times, let's see, negative 1u to the negative 1 power. So replacing, going back and getting rid of our negative exponent and replacing the u with x minus 2, we end up with this is our answer. So x squared plus the natural log of the absolute value of x plus 2 minus the fraction 3 divided by x minus 2 plus c. Well, that wasn't so bad. Okay, let's try this one. Okay, this one is proper, so all I have to do is figure out the factorization of the denominator. So x cubed plus 2x squared plus x. We can see it has a GCF of x, so let's factor out then x. And then we can factor that quadratic to x plus 1 quantity squared times x. And so we can rewrite our numerator. Check and see if you got your 3 terms correct. Remember how you did the repeating factor. Find your basic equation. We're going to let x equals 0, one of our roots. And we get a equals 6. Then we're going to let x equals negative 1, another root. And we end up with c equals 9. And then we're going to choose some other value of x. So we're going to choose a value of x. So I haven't used 1 yet, so let's do that. And when I plug in 1, I end up with b is equal to negative 1. So rewriting this will be integral of 6 over x dx plus the integral of negative 1 x plus 1 dx plus the integral of 9 over x plus 1 quantity squared. Okay, finding the derivative of each of those. We end up with 6, the natural log of x minus the natural log of x plus 1 minus 9 divided by x plus 1 plus c. Now you can do some simplifying on this because of our properties. Remember, with exponents, we can bring our power, if we're multiplying by constant, we bring it into the logarithm, make it a power. Remember, subtraction becomes division. So you're probably going to see the answer written like this.